In this video, we're going to take a look at what are known as improper integrals. But before we do so, just a quick review of the fundamental theorem of calculus, which states that the definite integral from a to b for some function f of x is equal to big F of b minus big F of a, where we state that that big f of x function is the antiderivative of our little f of x function, and the only condition that needs to be met is that f of x is continuous over the closed interval a to b. And the purpose of the fundamental theorem is to help us calculate the finite closed area bound between any function f of x and the x-axis. But in this video, we're going to take a look at a weird example and say, what if we wanted to evaluate the integral from 1 to infinity of the function 1 divided by x squared with respect to the x-axis? Now this might sound like a very strange thing to even try to talk about, but let's take a look at the graph for this function. Here's the function 1 over x squared, and we'll bound the area under this curve from 1 going off to infinity. Now this area may seem like it should grow forever and ever, but consider the limit as x approaches infinity for that function 1 over x squared. It would equal 0. So let's think about what that means in terms of the area under that curve. So the question becomes, if the limit of this function as x approaches infinity equals 0, does that mean this area eventually closes? Or to think about this question in another way, if the limit as x approaches infinity equals 0, does this mean at large enough values of x, at some point, does area stop being added to this region? And this brings us to the concept of an improper integral. And an improper integral is a definite integral with infinity serving as at least one boundary on the integral. But there's one major issue with improper integrals, and that is infinity is not an actual number. So to calculate an improper integral, we calculate those using limits. Since infinity is not a defined value, then these integrals do not exactly follow the fundamental theorem of calculus, which requires both boundaries to be constant numbers. And so now let's see how this process will work. Let's go back and use our original example, the integral from 1 to infinity of 1 over x squared with respect to x. And what we're going to do is we're going to set this up as the integral from 1 to b of 1 over x squared dx, where b is a constant value, and let b approach infinity using a limit. And now looking at our definite integral, we've solved one issue. Both boundaries, 1 and b, are constants. We already know that 1 over x squared is continuous from 1 to any larger value b. So this definite integral will follow the fundamental theorem of calculus, which means we can evaluate it. This will be the limit as b approaches infinity of our antiderivative, negative 1 over x, evaluated from 1 to b, which will be equivalent to the limit as b approaches infinity of negative 1 over b minus negative 1 over 1. And notice, this negative 1 over b, if we let b approach infinity, that term will approach 0. And the negative of negative 1 over 1 will be a plus 1. And so this limit, and subsequently the integral from 1 to infinity of 1 over x squared with respect to x, will equal 1, which is a somewhat surprising result. At large enough values for x, or at large enough values for the second boundary on our definite integral, the area actually becomes finite. Or the other term that's going to start coming up is the area converges to one single value. So let's finish by taking a look at one more example as a contrast to that first situation. And in this example, we'll look at the integral for 1 over x dx, also from 1 to infinity like we saw in the first example. And we'll solve this by setting up the limit as b approaches infinity for the integral from 1 to b of 1 over x with respect to x. The function now has constant boundaries, and 1 over x is continuous from 1 to larger values of x, so we can evaluate this as a limit as b approaches infinity for our antiderivative, which in this case is natural log of x, evaluated from 1 to b. So this will be the limit as b approaches infinity for natural log of b minus natural log of 1. So this will yield the limit as b approaches infinity for the natural log of b, since the natural log of 1 is just 0. And the natural log function, as b approaches infinity, natural log also approaches infinity. We get an area that is unbounded, an infinite area. Or what we say is that this integral diverges, and this area becomes infinitely large. But to look at the graph, we wouldn't see much difference between this and 1 over x squared. The functions look relatively the same, and even the area appears to be growing in the same way. 1 over x still approaches 0 as x approaches infinity. So the difference between these two functions becomes a point of emphasis in future lessons. This lesson is only focused on the idea of evaluating improper integrals, so breaking down this difference will not be done in this particular video. But just note that the difference between two functions like these does become an important point in discussing what are known as infinite series. That does it for this lesson on improper integrals, and thank you for watching.